Alright, hello everybody. Let's look at problem set 2. This is going to cover the Samuelson Multiplier-Accelerator model first, and then the second part will go over the Borrow-Gordon model, which, as we discussed, were like the two types of extensions to the Keynesian framework that we saw initially. So initially we saw the very basic aggregate macroeconomic framework that was the first big idea in what we could call modern macroeconomics. And we said that there's two big ways to extend that. One is to add individuals via maximization and assumptions about preferences. And the other way is to add time dynamics. So we'll look at time dynamics first. This is important because we want to be able to say something about not just where the economy is going to go, which is what the Keynesian analysis does with the ASAD curves and the ISTR curves, but also how it's going to get there. Which is what Samuelson wants to do with this model. So here's the model. We have a y, a c, and I, and a g. And question A. We'll do the ABC first in this video, and we'll go to the next ones next. So first it asks us to comment on the similarities and differences between this model and the IS model. So we need to remember the IS model, which started with y equals c plus I plus g, as all macroeconomic models do. And then we had a C equation, which was something like C0 plus C1 y. Maybe there were some tax things here, but it's not so important. We just need to have some intuition about the functional form. Here we had nominal interest rates and productivity, total output. Something like this, and then G is G bar. Again, I mean, well, we'll see what maybe you should take away from this. Yeah. Okay, so differences and similarities. So this, of course, we have the same y equals c plus I plus g in both cases. And in both cases, we have a c equation, we have an I equation, we have a g equation. Okay, so we're studying the same objects. Just we're going to think about them in different ways. First, we know that Samuelson, the multiplier-accelerator model, that said model? I don't think so. The multiplier-accelerator model has time. So of course, this is the big reason why we want to study this. So there's a first difference. I guess maybe we can make like columns. You know, these are differences and then similarities. Similarities, both are aggregate macro models. How do I know they're aggregate? Because there's no individuals, right? Because there's no preferences here, there's no optimization here. This marginal propensity to consume is just a thing that we invent. We're not making any claims about what do people want to do, why do they choose to consume this. We just pull out this number and we say that's the number. So neither has individuals. Okay. So MA model has time. Does the ISTR model have anything the MA model doesn't have? Well, yes. Here we have CT is a function of YT minus 1. Also CT is a function of Y. Okay, but here I is a function of the difference between YT minus 1 and YT minus 2. Here we have Y, we also have a Y, but we have this I. We have a price, something that's like a price. The important point here is that, like the price of capital, right, the interest rate, there are prices in ISTR, but not in the multiplier accelerator model. Okay, so there's another difference. Anything else? We can say that the ISTR is all in levels, while the multiplier accelerator considers velocity. Okay, where does this come from? This comes from this yt minus 1, yt minus 2. So if you recall, if we think about a car, okay, and we plot distance traveled against time, and we have a line, so the car is traveling, and we consider the difference between some t and some t, and we subtract this value here from this value here to get the delta d. Well, the amount, if this delta t is very small, then this will be the speed of the car. This will be the velocity of the car, right? And there is a sense in which differences are velocities, because we're taking something that is accumulating and we're splitting it into the rate of change. So the interest rate cares about the velocity of growth, whereas here, the investment, I apologize, I think I said interest rate. The investment function cares about the velocity of growth in the MA model, in the multiplier-accelerator model, whereas in the ISTR, it only cares about the level. It just cares about the absolute level of y. So this is all the differences. This would be sort of sufficient for question A. So question B asks, is this model, so we're just talking about the MA now, is this model subject to the Lucas critique? Justify your answer. We need to remember, what is the Lucas critique? The Lucas critique says that a macro model without individual preferences is not valid. Let's just be straight. Is not valid because using this model to do policy will change the parameters, will change the aggregate parameters, i.e. C0, C1, I0, I1, etc. Okay, so the example we talked about again in TD was if the government were to use a growth spending increase to stimulate the economy under the idea that, okay, we have a multiplier, so we're going to use growth, we're going to use government spending to stimulate growth, and then there's going to be a multiplier. Well then, people in the future will know that the government gives growth stimulus in certain times. And then this C1 parameter will adjust. Maybe they'll think, okay, if you give a stimulus in the future, then I can consume less today. Because now, if the Y goes down, I consume less, my C1 goes down, so Y now goes down, which triggers the government to do a stimulus, which gives me free money, right? So the households endogenize the behavior of the government. The government employs this model to make these assumptions, make policy. The assumption of the model is that C1 is fixed for all time, but the actions of the government by using this model cause C1 to change, which invalidates the model. And we saw that this is it's a type of application of Goodhart's law. Goodhart's law that says that a measure that becomes a metric ceases to be a good measure. Okay, so that example again was hours worked in an office. If you say that workers who spend more time in the office are more productive, therefore you make all workers spend more time in the office, workers become resentful, or they don't have enough to do in the office. Everybody has a different workload, so they just have to sit in the office, and then you've brought up the amount of time working in the office, but now the amount of time working in the office doesn't accurately reflect productivity levels. So not only have you made a wasteful policy, but you've also ruined your measure. You can no longer look at the number of hours in the office as a measure of productivity. And that's Goodhart's law, and it's very tightly related to the Lucas critique. And all of these are related to an idea called hysteresis. S-I-S, maybe that's S-Y-S. Please don't yell at me. Hysteresis is just this idea of model feedback. Okay, so is the multiplier-accelerator model subject to the Lucas critique? Yes, it is, because there are, as we already noted, no individuals. Okay, no individuals. Yes, Lucas critique. The word that you'll see in the macroeconomic literature is microfoundations. Microfoundations. D-A-T-I-O-N-S. Okay. When a model has microfoundations, then typically economists will consider that to be a quote-unquote valid model, because it's not subject to the Lucas critique. That's changing lately, but this is true for a very long time. If you go to macroeconomic conferences and you present your paper that has a macroeconomic model, many people will still ask you, where are your microfoundations? Because many people still care about the Lucas critique. They take it very seriously. So it's just something to be aware of. Okay, great. Number C. Number C asks us to write the reduced form. And yeah, we can do that quickly. We just have to make some space here. Let's delete everything. Ta-da. Okay. So number C asks us to write the reduced form of the equation by substituting it down to a single autoregressive equation, yt as a function of yt minus 1, yt minus 2. Okay. Okay, so let's do it. We're just going to, I guess the first thing is this is a functional notation. Maybe this is not so clear at first reading, but it's good to get used to this, that, people will write, like I'm sure you know f of x, of course, but then we can also write y of cig, of course. And here I'm doing the same thing. So you might think that this is like multiplication or something, but no, this is saying, give me a function of yt that has as arguments yt minus 1, yt minus 2. Okay. So all we're going to need to do is to substitute these three equations into this equation, and we're done. So I will use a new color. How about purple? And so I'll start with yt equals, and then let's bring in ct. We have gamma plus a yt minus 1 plus, and then we'll bring in it. I'll follow Khan Academy and do different colors for the different blocks. It is b yt minus 1 minus yt minus 2. And then gt, I'm going to commit to the bit. I'm even going to change it for gt. Seafoam green. gt is just g bar. And now, technically we're done, but we can make this a little more beautiful because we have a yt minus 1 here and a yt minus 1 here. So I'll want to distribute this b. We'll end up with plus byt minus 1 minus byt minus 2 for this term. And then we have an a here. So we'll take the a, we'll take the b, we get a plus b times yt minus 1. So our final answer is yt is equal to gamma plus g bar plus a from here plus b from here times, together we factor the yt minus 1. This is negative, so we have minus b yt minus 2, and we're done. Ta-da! Okay, and recall that this is an AR2 equation. This is an AR2, so autoregressive of order 2. And we can see that by defining new parameters. We can call this row 1, and we can call this row 2, and we can call this maybe row 0. And then we see that yt is equal to a linear function of only itself. in the past. Let's define a negative b, right? So we'll have a plus here as well. Row 2, yt minus 2. And then we also add a random error term, which is just normally distributed with some unknown variance, or some unknown standard deviation, as you like. Okay, so that's the first 3 questions. I hope that was all straightforward. I apologize for going slow. Thank God there's times 2 speed, right? I'll see you in the next one when we do the rest of this question.